Yeah.
get 50.
So far we have less than 30%, right?
So that's good, right? You can relax for almost half a semester and then suddenly work.
And then suddenly in like end of March, you're like, hey, in 2 weeks, I want you to make a project that's 50% of your grade. Yeah.
That's awesome, right?
And I don't have
Everybody gets less time. It's relative. It's fine.
What if they don't scale? Sure. Then
Nah,
what?
they should scale. Let's be optimistic.
So many stairs.
Yeah.
You can take elevator. Nobody takes elevator. It's
Yeah, it's
fast.
Aren't we young and
It's
strong?
over there.
So, like, elevator is...
Have you read the notification of it? If you can walk, please don't take the elevator.
But it takes like 2 seconds.
I know.
I mean, it's
So there's this other side of things as well, where you take the train, you take buses, maybe you're busy all day in the office. Somehow you gotta fit in exercise. Running to class quickly upstairs.
Do you do it twice?
Well, I mean, the way that's slower. Okay, yes, you're here. That's good. That's something. Okay.
So the paper got published.
Yeah. It's interesting. Sometimes a young student does not get published.
Publication is a bit of a lottery. It comes back after the fact sometime to pay benefits.
Yeah.
You'll find that, at least in my area even, there are papers that became best papers.
This is not mine.
That isn't, oh.
Like,
Oh. Okay.
I'm gonna put a strength on it.
So, yeah, so, it's happened that best papers get rejected like 7 times.
Yeah,
And because of
the
feedback.
one who came for Microsoft talk recently, she said that her paper got rejected so many times before taking a best paper.
Yeah. And it happens. It happens.
Well, it's very bad when it happens when you're trying to, get closer to your PG defense and...
This is true, this is true. Ideally, you want to get those publications out before your defense, but that happens. Okay, so just, yes. So point of order before we get going with things. There has been a request for slides, which are now posted online, protected so that only people in the class who've already seen them, already had access to them, are able to access them. Just so that we're adhering to student rights and whatnot.
Slides. Well, these slides.
In general. So I'll post them after presentations. Also, there's been a request for example critiques. If people are okay with me posting critiques, I can do that. I'll go through and find some of them and find out how to remove names from critiques, because there's got to be some magic PDF stuff out there that...
There is some.
Yeah.
But you can always recover it back.
Well,
You can actually edit the text of the PDF itself.
No, yeah, but there's something called you can hide in the same place in every PDF, but then you can recover it back as well.
you just
okay.
open PDF in the Word, just delete the name.
Yeah, so it depends on what you use to hide it. If you just like put a box over it, you can delete that, which some of our security agencies did because they were stupid. Anyway, let me...
So, seems like such a lazy way to do things. Like, let me put a box over. You can't see it. It's all redacted. It's the same as if I take like a black pen over it, right? It's like whiteout. Yeah.
So, being anonymous in a class of 9.
Yeah.
Well, I'm not going to post any that aren't as strong. I'll post the positive ones.
Okay.
Okay. But being anonymous in a class of 9, you're not going to have a baseline for comparison. I'll put it that way.
True.
So you won't be able to know what this signature is that indicates particular people.
Okay.
And I have found that, by and large, among the strongest critiques. There isn't a signature that says it was this person. Just to allay fears there.
Why did you write the paper?
It's pretty interesting actually. She said she never writes strengths and weaknesses. Strengths, right? So
Right.
Just look at the critic and say, sir,
We can figure out from everyone's writing style.
Or you can try to, you could watch,
Why
you get
did
the
you write
critiques
it?
passed back every week.
I'm a little
And
bit.
then just look at what it looks like.
Well, then you can say, okay,
I
well,
didn't know
this
that.
critique is only done, then you can like reduce
No, I
it
don't do
down.
Sorry, Nick, I'm behind a little bit. What critics we talking
That's a lot of
about?
Now we are ready to read for the one.
What critics we talking
He's
about?
Naveed.
What do you mean?
Like right now, you want to make our critiques public or something?
There's been a not public. There's been a request. If people are amenable to this, there's been a request for examples of good critiques.
Alright, if my critique is a good critics, make it public. I want everyone to see it. And it's better if it would be Googleable. It would be even better. Then it will. I'm a prominent critic, paper critic, and criticism.
Thank you. I'm a critiquer.
Like whatever. And people say, "Oh, please, Evgeny, critique our paper." And what's the problem? And then I will get prominence as a scientific paper critic.
It's not a movie critic.
See, new genre.
Is there scientific paper critique? Goodness.
Does it exist? That sounds like a cool job.
I'm one.
No, that's not.
Oh, we're called reviewers.
Yeah, paper reviewer.
We're anonymous.
Depends on the conference.
Like,
What do you think?
I give this paper 4 stars out of 5.
Okay, it's been fun for like a week.
It is on.
But I guess that's
It's
how
off.
conferences are. These are the 5-star
It
papers.
turned off.
And then you have a second tier conference, these are all the 4-star papers.
Please be nice to them.
Yeah.
Like start attaching bills to it, like staple some bills in between.
Yeah. Oh, you could put just because it's all digital submissions, so just Bitcoin address, you know, some big bribing through cryptocurrency. This could work well.
Maybe a QC code in there or something like that. There you go.
Okay.
Bitcoin exchange rate drops. You give me $1?
Well, that's what I was going to give you in the first place. I like that. Like,
That's smart.
or bribing with cryptocurrency.
Okay. Can someone let them know to re-enable this thing again?
We were too late to turn on.
Oh no, we were too late to keep the projector on.
Yes, yes.
Oh no.
Is it turned on?
Yeah.
It was on?
It was.
You just have to.
Now it's not.
Like 5 minutes. Yeah, there should just be like a button.
They fix in washrooms next door. Yeah, men's washrooms, totally redesigned. So you have the process will go better.
Wait, so we have no projector and we get to listen to that?
There goes the next one.
We'll steal somebody else's room. We'll kick them out.
Hello, you guys, please.
What happened?
Actually, he asked me how long would you like to turn on the projector. Which
You
is
should
interesting
know.
because after this there is no class.
Yeah, you can.
You can ask them for
1 hour.
We can steal their time. All right. We can steal screen
We can
time.
actually call them again after an hour and say, please come.
Okay. Let's.
We're
Okay.
trying to take back as much.
It's on. It's on. It's on.
Good.
Oh, we're
It's
doing
alive.
So we can discuss his paper for 2 hours.
Better not, because I have TA hours. Well, I scheduled TA hour.
TA hours, you can skip those.
Office hours?
Like TA officers, but so far no one ever came to like.
You can call them here.
What are you TAing?
Have you told?
886. Naveen is my student. Never even came to office hour.
Oh.
I
Because
sure
they're
hope
in
you're
the
doing
same
well.
office.
It's at least showing.
I'm like, I'm pretty sure he's been to a lot of them.
It all makes sense now.
The office hours, right?
Like, hell, I go to your TA.
So,
You have so many people in your office.
do you want a clicker?
We can use them.
Okay. Okay. I can give you clickers. It's fancy. Assuming I brought it. Yes, here we go. Yeah, yeah. Oh, did you want the?
No, that's fine.
So many technical difficulties.
We need to debug using the EM passes.
We could.
Okay. So, how do you turn this on? So yeah, this is AI, a lightweight system for tolerating concurrency bugs. Motivation, generally they are hard to expose, and existing concurrency bug tolerating tools at that time, whichever were made, had a few problems. Like they either, so there is a constraint types in which they handle the bugs, and most of them requires a rollback. So by rollback, what you mean is first you run the tool, and suppose the tool, if the tool crashes, they generally have checkpoints where they go back to and then re-execute the experiment. So what's the proposed solution? They thought that let's have a lightweight production run bug tool. So what it does is, it will not really debug it, but it will ensure that the experiments won't crash, your program won't crash. And how they do is by efficiently stalling the thread at whichever point they feel that you can have a concurrency issue.
Well, let's say it's not always crashing, it's just that it won't be. Not all bugs will crash the program, right?
Yeah, so these are concurrency bugs, right? So whenever there is a potential place where you can have a problem, it will just ensure that you use an interleaving mechanism to stall one of the threads and let the other execute, so that it comes to a proper program execution order. So requirements, so there are two things basically which would require for such kind of a tool. One is it should have a large coverage. So it should be able to handle most of the concurrency bugs, existing bugs. And the next is it should have a decent performance time, runtime. It should not be so slow that your program is like so slow that you don't want it to run anymore. So these two are like a critical requirement for a tool like that.
Does the runtime include the overhead as well?
No, overhead is during the testing, right? And this is during the runtime. So your testing time does matter.
I think this depends on what you mean by overhead. There's testing overhead and there's runtime overhead.
He's asking about testing, right?
I'm asking about the, if you add more code, then there's more overhead, right?
In terms of testing or runtime?
There are two different notions of overhead. Well, I think this is a good question to come back to once we discuss what the system actually does.
Sure. Don't forget.
So, so all the existing approaches before this tool, they generally use like three types of approaches. One was the always on approach, which basically constrains the program execution all the time, just like this tool, but there is a difference. The difference is that what they do is they create batches of all the atomic instructions which can execute at the same time, and then they interleave it using so it depends. The performance depends more on transactional memories and stuff like that. So it's not that fast, and it cannot handle order violations. Order violations is basically if a write should come after read, and when you use different threads, it just swaps the order, right? Which is not correct.
So I don't recall, but do you go through order violations?
Yeah,
and
it's
okay.
there.
That's
So yeah, we'll talk about it in detail in the next section.
okay.
So the second is failure recovery approach, which is basically a rollback mechanism. What it does is at each point of a program, at like certain points, they have a checkpoint. By checkpoint, we mean like it saves the state of the program. So like if there is a fault which occurs later in the program, they go back to that checkpoint and then re-execute it. Traditionally, what happens in our traditional database systems. But that's expensive.
That's rollback, right?
Yep.
That's the rollback.
That's
The rollback.
yeah, they roll back. But that's expensive in terms of runtime.
So it somewhere in the paper it says that the rollback requires hardware support.
Yeah, so
What is that?
it might require, what happens is like, suppose by checkpoint you mean you save the state of a program, right? By state you mean you save program counter and all the variable names and stuff like that. So generally hardware support is required in terms of that. Say if you have a single core and single threaded system, you cannot use that or something like
So
of that sort.
in general, what you're looking at is implementing a notion of transaction, right? And so this is the idea of a transaction where either this completes successfully or you have to roll back. And there are hardware-based transactions and software-based transactions. Hardware-based transactions or hardware transaction memory is a little bit more recent. It's not as widely adopted. And the idea is that you should be able to be more efficient if you have it baked into hardware. But by and large, historically, implementations have been more software directed. It's not necessary, but it makes things more efficient.
Third is your post-mortem approach. What it does is basically if your code crashes or if they find a bug, they train your tool for that so that in future it does not happen. So that's same as any traditional testing mechanism. The new approach which they proposed was basically anticipate bugs before it occurs. So generally there is a notion of a turning point when you are executing two different threads which are supposed to execute in a particular order, and if the order changes, if there is a difference, then there is a point, a specific point where you can exactly stall the thread so that the program fault does not occur. We'll come to that example in a few slides after this. So basically the notion is, can we anticipate the bugs before they come? And that's the intuition. There is a problem. If it is too early, then you might get false positives because you're stalling the threads for no reason, which will delay the program execution time. And if it's too late, then you might miss a bug. Then by traditional methods, you'll have to checkpoint or rollback, which is again expensive. So you need to find that specific point and you need to be precise for that. So what are the most common bugs generally found in these scenarios are atomicity violation and order violation.
Sorry, just a question. I thought the turning point could be the instruction that executing that instruction causes the concurrency bug. So I thought that would be exactly the turning point.
Yeah, so there were like initial issues. What people thought was if you just look at writes, it is sufficient. Because generally reads don't cause error, but that's not the case.
So it depends on programmers.
Yeah, so right, so there are cases where even reads can cause errors, and that's where most of the tools went wrong.
I think there's some notion here, which is the fact that the instruction that causes an error may not be the last point before the error is inevitable in a given program. So it's in general, the writes are necessary to have the actual error occur. In a very real notion, the writes cause the error, cause an atomicity violation or an order violation, and that will be the actual cause of the bug. But the last point before you can avoid that cause may or may not be that instruction.
Why not? Can you give an example?
Yeah,
We'll see.
We'll see that. So that's the thing. Like most of the tools, they were looking at writes, and they would miss the point where you could actually stall the bug. So the thing is when you.
But I don't understand because I think even if the programmer gives the ordering, you can. So that read could be the instruction that causes the bug.
There's nothing. If you have two reads of a variable, There's nothing incorrect about that. You can read a variable twice, and there's no bug there. It only becomes a bug when you actually have some sort of write in the mix that causes a conflict.
But the programmer can constrain that, like impose that 2 reads are blocked.
No, I mean, there's nothing incorrect about 2 reads of a variable. It's only in this context of the rest of the program where you have some writes involved as well, where there is a bug. Because if I have a variable and I read it twice.
No, I know in terms of concurrency, but I thought the programmer can do that. Like you have that ability to do that in the implementation. Like logically, there's no.
That's a slightly different thing. That's a slightly different thing. Where the programmer can say any writes or reads of this particular state, this particular variable are relevant. That's an annotation issue. We'll come back to that. We've got some conditions.
Yeah. So, what do you mean by notion of a turning point? Basically, so the first one, if you see the A part, is the correct run, which is supposed to happen. Like there is a variable X, and you are trying. There are 2 threads who are doing read and write, and that's the order it should follow. Suppose if the read goes above the write X over this point, then it causes a write after read, is it? Yeah, so it causes an error, right? So here atomicity is the problem. Those 2 transactions should be atomic for these threads.
So what is the incorrect outcome in the second scheduling of A?
The new value written gets overwritten by the other one.
Yeah. So there's a lost update.
So again, the thing is that here, if you see that read is the turning point. So most of the tools, they were trying to stop it at the write, when the write comes. Now the problem was it was just too late for them to do anything about it. So you have to roll back, which is expensive. Whereas what they tried to came up with, if you can just stall the thread at that point, at that read point, and let this thread execute.
Is it before the read?
Yeah, so that read is the point where you want to stop the thread from executing for some time, so that it stalls. And then the thread 1 will execute, and after that thread 2 will execute. So just stalling for some time can actually save you from the bug. Whereas in other cases where these other tools were working on, they were trying to look for writes, but when you look for write, it's just too late.
Because the read has already been done.
Yeah. And the second one is an example of an order violation where a read should happen after the write, but the order is swapped. So most of the tools, there are a few tools which were proposed which don't handle this order violation.
In what particular case, like, should the read happen after the write?
So this is
Why
like
does it
if you're
say-
using a variable as a signal between 2 threads. This is the sort of thing you'll see.
So it's about scheduling threads also, right? So
But in reality, how you would enforce it? By stalling thread 2?
yeah, you just stall thread 2 and it will be fine.
So, is it possible that we can call the write function as well instead of the read? I mean, do they specify that?
No, so the correct order is say right after read.
Okay.
It is a notion of a correct order. If the notion of the correct order is the first one, then it should follow that order. So it depends on the testing part, like what notion do I. So during the testing phase, we know this is the correct run, and these are the orders which it can follow.
Right.
So that's my notion of correctness, and I'll stick to that notion.
Which we'll get to.
So had it been the other way around, it would have stalled the write?
If it learned that the correct order were the other way around, then it would stall the other way.
Yeah, well,
So the main idea is stall a thread right before the turning point to get around bug manifestation. And for an instruction I that accesses a variable V, you just capture all the instructions which are allowed to access V right before I from a different thread. So basically what we are saying is whenever you read or write, it's just like loads and stores in memory. So all you're looking for is loads and stores. Whenever a load and store comes for a particular variable, you just look at which address it is accessing, and you will look at all the variables, all the loads or stores which are being accessed by a different thread for the same address just before any other loads and stores in this thread. We will see an example. It will become more clear. So basically all it does is during the testing period it learns the ordering, and during the production run it automatically stalls the thread if it finds that this is the turning point where the bug manifestation can happen. So a lot of it depends on the testing phase, how the testing is being done, which may not be exhaustive. So a few definitions first. Basically, SY is a static instruction, which is like your source code. So whichever source code you write, there are lines of instructions, right? So they are SY. Okay. And IXSY is a dynamic instruction. By that we mean, say if there is a for loop, and inside a for loop there is an instruction SY, then when you run it dynamically, it will execute again and again, right? So it's a different instruction, but statically it's the same instruction line. So yeah, so IX is the instance, SY is the static code. The remote predecessor. So there are three conditions for a remote predecessor. By this we mean that if you have an instruction, you are looking for potential instructions from other thread which are trying to access the same memory location. We'll see an example, but okay, let's see an example first. So this is a notion of remote predecessor. So what we are saying is there are seven static instructions in the source code. You have S1, S2, S3, S4, S5, S6, S7, and I1, I2, all these are instances of the same source code. So if there is a loop, then you will have the same static instruction name, but your dynamic instance will differ. Okay. So if you look at this, if we say this is the correct order, or this was the test run, and we know that for a fact that this ordering is correct, in that case, what it's saying is that I1 S1, if there is a write of a X, it is dependent on your I3 S3 of a read. So basically what is happening is that what we are just trying to say is that if you look at R3 I1, that is nil. So basically it's saying that before I1 nothing should execute from a different thread. And when you say R3 I3, then it says S1, which means that if I3 is executed, then S1 should execute before I3, always from a different thread. Only this can execute from a different thread in case of I3. Similarly for I4, I4 is reading Y variable, so you will just look at all the Y variables, which you will look at the first write or read from a different thread, and I4 is basically saying that S2 can execute before I4.
So nil means before I1, and so I thought nil means this instruction can be executed.
Nil means is the first one to execute.
Yeah, I thought it means this instruction can be executed before any X.
So when that is executing, it means that there should be no other instruction which should execute before that, in terms of same memory location.
How about the other way?
About that one.
Okay, about the other way.
Yeah.
This instruction can be executed before any instruction.
So,
Yeah.
You say?
Not exactly, no. Because
It should have the same memory location.
it depends on what the observed correct predecessors are for that other instruction, right? So if we look at this, we can see that it's okay to have nothing execute before S1 that accesses X, right? But this doesn't mean, the fact that the predecessor of S1 is nil does not mean that S1 can execute before anything else. Having S1 execute before S7, for instance, is not correct.
Why S1 is writing X,
The
S7
order
is
will
reading.
change, right?
There should be nothing
Right.
before S1.
Well, there should be nothing before S1, but this doesn't mean that S1 is an appropriate immediate predecessor of S7, because we can see from this, the only thing that we know is that S5 can precede S7.
Oh, That's from the training? Or?
Exactly. So far we haven't actually discussed the training, I think, so there's this ambiguity. We're just discussing this notion of the remote predecessor.
So this is just a definition of remote predecessor.
Can there be an instruction in the thread 2 that accesses the same memory location before I1, I2?
Before I1
Or I2, anyone?
There can be, but like that is not being used as a testing pattern or something.
Yeah.
So we don't know about
the question is what accesses across threads.
So that's what my question is. If it's in the same thread, then we can use it, right?
Then it's irrelevant.
It's
If
irrelevant.
it's in the
We don't
same
care.
thread, then it's not a concurrency bug.
We don't care about it. So technically, if you look at it, all you want to do is look at 2 memory accesses for each variable which happened before
Why
that.
only 2?
From different big threads.
Why 2?
Because so by 2 we mean that one for the current one and one which you're looking for a different thread which is trying to access the same memory location.
So it may or may not be the current one. This is something that I think is actually clever. So you always want to track the most recent access from a different thread to the same location, right? That's how you can identify these sorts of things. So the interesting thing here is that 2 is enough if those 2 are from different threads, because at least one of them will be from a thread that is not the current one.
Yeah.
And so 2 is enough, so why collect any more?
How that, sure.
Because if those most recent 2 accesses are from different threads, one of them could be from this thread, but at least one of them, if they're from different threads, is not. And so that will give you a notion of what the predecessor could be.
What if both of them are from different threads?
If they're both from different threads, then just choose one, it doesn't matter. Choose the most
Yeah.
recent one.
Choose the recent one. It's
And
fine.
if they're both from the same thread?
They can't be. You make sure that
And
you
it's not
record
common.
2 that are from different threads.
So that's the idea which makes it lightweight.
Yeah.
Because they are not storing big histories of different thread addresses. They just store 2. And
It's kind of clever.
Yeah. So then the belonging set, basically we saw what remote predecessors are.
Mhm.
So belonging set for say S1 is nil. Okay, so basically R3 I2 is equal to S1. If you look at it, R3 I2 is S1, yes, and R3 I4 is S3, right? So now if we talk at belonging set for S2, it means that all the instructions which are predecessors of S2. So basically you will just take a union set of all the predecessors of static instruction S2.
Okay, so that's the low level. Now let's take the standard question. What is the intuition? What does it say at a high level?
It's belonging set.
Yeah. What does it tell us?
So it tells you the instructions that can be executed before the instruction you're trying to execute. If it's not there, then it's a violation.
Okay.
If it's there, then it's okay.
Okay. So essentially you've got all your training runs, right? And you can look at all the correct executions or the passing runs and say, well, these pass, so I'm going to use them as exemplars of good behavior. And so I can look at all the instructions that access a certain address immediately before this one or something like that. And if those are in my training set, then we'll make that allowable. We're creating a whitelist of allowable instructions, allowable predecessors. Is that still opaque?
It says rules for execution.
Hmm?
Rules for execution.
Yeah.
Rules of what, how the program is allowed to flow.
Yeah, so are people familiar with the term whitelist? Okay, okay, so you can have a blacklist and you can have a whitelist. A blacklist says this is a list of things that are not allowed. A whitelist says this is a list of things that are allowed. So what this is doing is creating a list of the instructions that precede one that are allowed.
In the correct.
Yeah.
So basically later we'll come up into cases where it's highly configurable. You can add your own set of rules, add to the whitelist, and you can change the behavior of how these should execute.
Yeah.
Which will be used for performance and stuff like that, where you can like decrease the amount of bugs it can handle or increase the runtime based on what kind of training you want to do.
And this is, I think, the question that you asked earlier. You know, the notions of how you can configure the whitelist in some way or another. And that's what you were looking at before. You could say, well, all accesses to this variable I want to add to my either blacklist or whitelist or something like that.
So,
Yeah, but you want to start off with a basis based on the training before you configure stuff.
So all you want to do is based on all your test runs, you will keep on taking a union of all the predecessors which you gain from all your training, and just add it to your belonging set. And when you do a final run, a production run, you will look at this belonging set and decide whether the turning point is reached or not. So if there is a violation to that belonging set, you just stall that thread which is causing the violation until it is resolved.
Sure.
So this is one of just an example of how this thing works. Basically, so if you just look at the correct run 1, the R predecessor 1 of I1 is equal to nil, and R predecessor of I1 for I2 is also nil, and for I3 is S2. That's clear, right?
Yeah.
Okay. The second one, similarly, for the second one, I didn't really understand why they said that is bypassed by NF condition if there is an intermediate.
What was that?
The last one.
So in the code it was written somewhere that if you show the corresponding code for this one,
Yeah.
there was this if condition which was getting bypassed.
Okay.
It
So
doesn't really matter.
yeah, so it doesn't really matter at all. So basically, you have these R pre from first run and second run. So your belonging set is just the union of all the R predecessors across correct run 1 and 2, which you form. And then during the incorrect run, if you see your I2, R predecessor I2 is equals to S1 in this case, which is not in the belonging set for S1 over there if you look at it. S1 can only have nil and S3.
Okay. So what's the solution then? This is an observed atomicity violation. People agree that we've now seen an instruction that is not in our belonging set.
Yes.
So you just stall the thread which is causing the violation.
Okay, so what does that do?
So it will just pause the thread.
Okay, okay, so
Pause
in the context of this example, what happens?
The write will be stalled until the thread 1 executes.
Okay, so we
And then
hit
write
S3, we observe that it's not in our set, and we just wait until we get something that is in our set.
And so it says it checks it again.
So
When does it come back to that?
what do you
So
mean?
it checks this every instruction as and when every instruction is executed, right? So when an instruction is executed, it will look for that.
Yeah. So what happens then is that it'll just stall that thread for a little while, and it'll come back, and we should actually talk about this. We should. This is one of the things where I want us to look at the algorithm. Although maybe this fits in nicely with your following slides.
Similarly, order violation, write should happen after read, and if the write happens before that, it's not in the belonging set, so it will stop. It's pretty straightforward.
So we may pass in the last slide. In the third example, the incorrect run, which thread is stalled?
Thread 2.
Thread 2.
Okay.
Yeah.
Because
That's exactly the issue. Why
I
I went
have
through
a
the examples.
question about starting the thread. So what if we have like 10 threads and 8 of them are writing at X, so the data is eventually one of them would write in that, but what if we stall one and then another one?
Whichever
how
are
do
causing
they
the
handle
violation,
that?
you will stall all of them and let the other thread run. So there are 8, maximum 7 can cause violation, right? You install the 7, let the first one run, and then the next time maybe 1 or 2 will not cause violation, you will let them run, and so on. What the problem can happen is
It says it installs one thread.
Well, it looks at every access, right? So it looks at accesses across all the threads. It's a very local reasoning process. That means that in any thread, if you have a predecessor that is not safe, then you'll stall that thread. So you can stall as many threads as you want. Because it's very local reasoning.
Okay, so if 10 threads write that, okay.
Excuse me.
Yeah.
The B said that we obtained from the training phase doesn't necessarily show the correct behavior of the program.
No, not always. So your testing is accurate, obviously, but the thing is there can be correct runs which are not part of your testing set. And it might happen that it will stall for like a long time and
we
will
should-
never end up.
We should also come back to that question about whether our testing is accurate too.
Yeah.
That's something that they kind of skirt a little bit. There's some other things, there are some subtle issues in here, which we'll see how much time we have for.
It sometimes may there be a bug, but it does not infect the output, so we can classify
Yep.
the predecessor as.
Right,
Yeah,
that
that
could
can
happen. So your training set is, it's a question of how good it is. It's gonna be approximate. You could end up having something where you have an incorrect ordering, but in the runs you have, it doesn't affect the output.
But in theory, you could put more rigorous testing on your testing set.
Yeah, so what they claim is that you could be smart about it and look at only those areas which are like you know that these are the areas which can cause bugs and just test for them. Also, there are examples where they say that generally a well-tested program does not have bugs in the hot region of the code. So basically what that means is generally the most executed runs are not generally.
That's more of an efficiency thing though,
Yeah,
as opposed to a
that's-
practice thing.
right.
There are some issues with that as well, where maybe the issue is the interaction between hot and cold. And I'm not entirely convinced that focusing on cold won't necessarily.
So that's a trade-off, right?
It is, but it means that their claim about the fact that bugs lie in the cold region doesn't necessarily prevent the hot region from playing a part and needing to be instrumental.
Yeah. That can.
But I think maybe we should move on.
So order violation implementation. So basically you have a source code. It goes through a AI prepared pass where it looks at all the thread ID and it gives an ID to every loads and store, which happens in the memory, assigns it to a variable. You get that load LD1, LD2. Then it goes through a trace pass where it creates a log, which is the instrumentation phase in everything, where they create a log as to so there is the point where they create this notion of belonging set, where you know that okay, these are the instructions which can execute and these are those which cannot execute, and then they store it in a, so they create a recording or a data structure where they store all these notions of correct behavior, and that's the testing phase. And during the production phase, you run the code, this instrumented code which you got from after AI trace pass, and then use it during the AI tolerate pass to look at the correct behavior. And if there is something wrong, you just solve the thread at that point. This is something. Performance bottleneck. In-house testing cannot be exhaustive. We talked about it already. So it is possible that only the correct interleaving is untested, and it might stall forever. So they propose a solution.
Why might it stall forever?
So basically, not stall forever, but basically it will try to execute and it's not in the correct behavior, so it's a violation, so it will stall.
Why might it not be an incorrect behavior?
Because it's not tested, it's not in the training phase. So there can be a certain order which is the only correct order which is possible, and it's not there in the testing phase. So you will end up just running it again and again, it will not end. So they have a threshold stall time for forward progress. What they see is, okay, if they wait for a certain amount of time, and if they don't find any correct behavior, it will just log it somewhere that, okay, we found this error, this might be a possible error, and then they log it and then they move forward.
This is not an uncommon solution, right? So have any of you seen solutions like this before, say in common synchronization APIs or something like
Operating
that?
systems, you have deadlock issues where they have a forward progress.
Right, so usually you've got things like time to mutexes or something along those lines, which is analogous. Roughly the same solution.
So slow production runtime for applications with large heaps, where you have large intensive heaps, like a lot of memory access is happening, and a lot of there are a lot of shared variables across various threads that can reduce the runtime of this application. And when there are a lot of groups over that shared memory, even that can have a problem. But still, what they claim is that they ran Apache, which was having the maximum runtime overhead, testing overhead of 1613%, which took almost half a day to test.
No, it's not Apache, it's a benchmark.
So there are a few subtle things there.
5,000 for Apache, that's what they say.
That's how many runs.
Oh, that's execution needed.
That's
for
during the training.
Yeah, that's the training part.
This isn't
This
the
is the-
Apache
okay.
overhead.
Yeah.
So that's one of the HPC benchmarks,
Yeah.
or one of the scientific benchmarks, sorry.
Yeah.
Yeah. So for interactive programs or for desktop applications, server applications, and whatnot, their overhead is just really low without any sort of need for the bias stuff at all.
Yeah.
Why?
They don't have shared access.
Okay, so they only need to instrument accesses to shared variables, accesses to the data that are shared across threads. And it turns out shared variable accesses tend to be relatively uncommon. In basically anything except very compute-based kernels. That tends to be true. So they don't need to instrument many of these applications, so they get low overhead. It's only when you have things that access a lot of data in hop loops that you really have to instrument a lot of accesses. Yeah. So for most applications, they have less than 1% overhead.
So, yeah, so they talk about this bias testing with custom instrumentation strategy for reducing these overheads.
I have a question. The bias was the same thing as the threshold?
Is rough.
Threshold is for forward focus, right?
What
Bias
is
is you compromise on the
Two
testing.
different notions of threshold. They had this counting threshold for how many times you retry inside the instrumentation. They also had this other threshold inside their bias system where you could say you look at the coldest, X portion of the code, and that's another threshold. So they've got a few different thresholding systems there.
So they proposed a few of solutions for reducing the testing overhead. One of this was like in a well-tested program, bugs usually don't occur in code regions. That's what they claim. I think they cited a paper for that.
Yeah, and that's true. In general, that's true, and it makes sense that it's true. The question is whether or not there's interaction between the hot and cold regions.
Is that is that frequent?
Don't know. I mean, that's it's an unknown issue.
I have a question, and the training overhead is also part of the total.
No, it's a different overhead.
It's a different overhead.
So you've got the training overhead, which for Apache took up to half a day. The idea though is that you train for half a day and then you deploy your application. And the deployed overhead is low.
Because they are storing only shared variables, and they're storing only two.
But that's still okay? Like the training overhead doesn't matter?
Half a day of development time is insignificant. You can waste half a day trying to understand a bug easily. I think you can waste days or weeks trying to understand a bug. So,
especially if it's paid time.
I think there'd be maybe some other factors coming into play. Yeah.
So I have a question regarding the paper. So when they tested 8 patterns of concurrency bugs,
right?
Have they tried to address the deadlocks or incorrect placed critical sections or mutexes? I haven't mentioned
incorrectly placed mutexes or critical sections will lead to these types of bugs. This is a lower level formulation of those issues with respect to atomicity and order. This doesn't look at deadlock. Deadlock is a separate issue. And then I did have some other papers cited inside the double locking assignment at the end that discuss about some of the newer deadlock oriented approaches. This doesn't so much look at deadlock. It does look at any sort of atomicity violation or order violation. So incorrect mutexes would generally cause an atomicity violation, unless it's really incorrect and again deadlock.
Can they use the same average for data rates?
A data race is a type of atomicity violation. Yes.
Right. Okay, so you need to.
Yeah.
Okay, they said their tool does not handle a particular type of bug which was stated in Bugaboo, where different threads try to access the same region again and again, like multiple access with 2 threads on the shared region. It's something I didn't look at.
So I think the problem there is in terms of the way you phrased it, you just described all atomicity violations.
No, and there are no logs, I guess, for that.
None of this takes locking into account.
Yeah.
It's agnostic of
I
locking,
know,
which
it's
is
something
good.
which I did not understand.
Because it's based entirely off of the ordering, the memory orderings observed. Let's see. But I do think there is this issue as well that, you know, if you're not careful about things like propagation, you could also have incorrect allowed accesses, right? Whether or not an incorrect interleaving or incorrect ordering leads to an observable failure, that's another big issue as well. It's just unknown. Do you remember where the bugaboo portion was?
4.3, that's all.
4.3. I don't see anything there that's relevant.
Yeah, 4.2.5. Last paragraph. AI cannot detect a synthetic bug described in Bugaboo, in which 2 threads repeated access to a shared variable must be interleaved. But no code constraint enforces the interleaving.
How? I guess that's why it's.
I think I'd have to take a look at that in order to. I don't actually know that precise bug. Oddly. No. But yeah, that's too vague to be concrete about it.
So what is the difference between just forcing an application to run in a specific way? Like, all right, here's your here's your whitelist. This is all of the possible execution ways you can run this program.
Mm-hmm.
If you do anything else,
and this has been proposed. This has been the issue there is that essentially what you're doing is shepherding underlying behavior.
Yes.
And that's even called shepherding. That's a term for it. This gives you more flexibility, a little more flexibility. You're not saying there must be a strict approach. Often with shepherding, what it's equivalent to is saying that for chunks of the code, here are correct interleavings of the chunks. And so it gives you this coarse-grained concurrency, but you don't have this fine-grained interleaving capability.
That was the first approach.
So what this is doing is this fine-grained learning of which instructions are reasonable. And one of the interesting things they found is that you can train to a certain threshold past which you learn all of the actual correct interleavings that are observed in practice.
Will the interleavings change if you move to another machine? Like you teach on machine
They could. This is a potential source of bias. In general, if you train, the idea is that if you train enough, you'll avoid this, but it is a potential risk, absolutely. Even the fact that you're adding instrumentation creates an observer effect, right, which could bias the interleavings.
With more training, since you're only recording 2 memory addresses, does your production overhead never goes up? It always goes down. Is that true? With training, more training, it does.
It should. I mean, so I would be a little bit careful about saying that because there is an issue about, one of the things I asked earlier about how they're efficient is that they only they only instrument shared variables. They learn which variables are shared through training as well.
Oh, okay.
And so you might learn that more things are shared.
Yeah.
Now that means you'd be more correct, which is good.
But you would also have higher order.
Yeah. Now, there's a fair likelihood that it's yeah, we whatever. I don't know. There wasn't a whole lot more left, right?
Yeah, we can have it for more.
We can. I mean, if people are interested. People, okay. Yeah.
You can take your office hours.
Or half an hour, 1 hour.
Yeah.
I need your office hours right now.
1 hour or half an hour.
In the class.
Sure. No.
How much should I ask?
That sounds good. That sounds good. Order
Half an
another
hour.
half hour of this projector pizza.
Half an hour?
Yeah, really.
But it was the end of the paper.
Well, I mean, there's some other stuff we can talk about. I want us to look at the actual instrumentation, based on the fact that people haven't been reading the more complicated parts of papers, apparently. I want us to actually look at the instrumentation they do and discuss some of these things.
So natural defense mechanism.
The part that the programmer can do some.
I mean, like the part they implement, right? Like the algorithm they have. I want us to look at that, but I also want us to look at the comparison with some of the other techniques a little bit, just to get a real intuition for what they do that is different. What is their contribution, and how are they similar? So that you can get a feel for, again, these baby steps that occur along the way of research. What were we talking about right before catastrophe struck? Learning shared variables.
That's it.
Yeah. So they don't know the shared variables conservatively. They're approximating, they're under-approximating the shared variables based on the tests.
Why is that? Why don't they just get them all?
Because it's hard, because of alias analysis.
Oh, okay.
Yeah. So in order to learn which things can be shared across threads conservatively, you'd have to do static analysis. And you'd be conservative, and it's expensive and imprecise. So they have a pragmatic approach, where they learn based off the observed tests which variables can be shared across threads. There is static analysis that can do that sort of thing, called escape analysis, which figures out which variables escape one thread into another and so on. And so you can do that sort of thing, but it adds a certain element of imprecision. So you've got to approximate one way or another, and they chose under approximation, which leads to better efficiency, but a chance for false positives in their case.
So the thing is, even in false positive cases, they just solve, so which will reduce
Yes.
the bug. So the only potential hazard is where you have bugs which are not solved by interleaving.
Oh,
Okay.
How do you get a false positive if you don't know it's a shared variable?
If you don't know it's a shared variable, then you.
It's not instrument.
Oh, that's true. That's true. False negative.
Yeah,
False negative.
in that case you can't.
So false negative, you're not installing this as kit.
Yeah. So if you don't execute code, then you might not recognize. What was it?
Can I leave? I have a
Sure. No, you're all prisoner.
Got that on video.
Yeah. What was that?
Yeah, they didn't talk about false negatives.
There was some stuff about false negatives.
They're easy. You just go back to the original point that you would have had anyways.
But again, that can be solved, right? By instrumenting it again. You just have to add it to the whitelist.
Now remember the false negative issue. The false negative issue is precisely the fact that you could add incorrect things to your whitelist. Right? Because your tests may pass even when the interleaving is incorrect. That's where the false negatives come into play.
Oh, I see.
Okay. So they're introduced into the list, and it says it's allowable, but it really isn't.
It shouldn't be, right? just because you coincidentally got the correct result with an invalid interleaving. The bug didn't propagate, and so you add that to your list. Otherwise, you have the false positive issue. And they solve that by timeouts, which is acceptable.
So
again,
is there a list of concurrency bugs for all the benchmarks you have used? Because it's
They
highly
created
difficult to tell, yeah, it's very difficult to tell that how many did you actually catch and how many.
So here's a notion of best effort, essentially. We don't know how many concurrency bugs there are.
So unless like someone else produces papers on these benchmarks, we won't know actually how good they were.
Unless someone else manages to improve on them, we won't know that they missed anything. Because the issue is that finding concurrency bugs is hard, and it's not feasible to do conservatively.
Even the search criteria. Did not mention more on the search criteria they used to find if the bugs have already been reported.
But that's more determining whether or not these bugs that they have found are real and new. That actually isn't too hard though. The developers themselves of those programs are the ones who would validate that and either provide a patch or not. And so the bug databases for those programs will determine whether or not the bugs are duplicates or something along those lines. But the issue of knowing whether or not they have found all of the bugs is difficult because that knowledge doesn't exist. Knowing how many bugs there are, especially in a program like MySQL, which is just pathological, we can be nice and say that MySQL is a little bit messy and ad hoc, and has a reputation for bugs. I mean, that's simply the way it is.
Is that because of MySQL, or is that just because large database applications?
I mean, you can look at Postgres, and Postgres is stronger in this regard, definitively stronger. So there are substantive differences. There are also substantive differences in code quality between the two. So, you know, that's just the way things are. Yeah, so knowing how many bugs there actually are in that system is just tough. But I wanted us to, before people left, I guess, since people are getting ready to leave, and you can leave at any time. That's I want us to take a look at the actual instrumentation.
ABI or?
Well, let's take a look at their algorithm. Just because we did take a look at their algorithm. This is. I'm gonna break out.
That's over.
Okay, now let's. One of these should have schedule.
And I may not read the algorithms in the paper, but if I were to implement it, I would go back and read them.
Well, that's something. I'm glad you wouldn't try to implement it without reading the algorithm.
Well, that's what it's there for. If you choose to, then it's there.
Well, the thing is, though, if you don't read the algorithms and you don't read the logic, then you can't poke holes in them. You can't understand how good it is. So you wouldn't be able to notice things. I mean, if you're not careful when you go through it, you can't notice things like, oh, if the testing includes something that doesn't propagate, then they might have issues there. They might have definitive false negatives where.
I feel you need to be an expert in the system to be an expert in the domain.
I mean, that means you're basically giving up on the material, though. You're setting a bar for yourself that's low and saying, let's not try harder than that.
That's an accurate description.
Okay. So if we
the
look at
highest standards, right?
Something's not good.
And why are they using a break in the else part?
why not?
Wouldn't it break loop?
But that's, I guess, the.
It's good. You.
That's what you want, right? You want to get out of the threshold.
Okay.
You want to continue the.
So let's maybe walk through this. I think that this question indicates that people should be going through the algorithm, right?
No.
You should open the source code and look into it. This is the true way.
You've only validated my point. Okay.
No, actually, they should go through the break when.
We should look at the source. We should look at the sample.
Well, if we look at this, right, this is a guard, which means that, so before every memory access that is relevant to them, you're going to have this, right? What do? Well, we get the access ID, we get the current thread ID, and then we have this bounded number of tries to stall to get into a correct interleaving. We find out what our predecessor is. If the predecessor isn't allowed, then we report a violation. So what happened? Why are we breaking?
You want it to work?
You want to get out of the threshold.
The predecessor was
Why?
allowed. You're allowed.
Because it was allowed. Yeah, high level, right? Don't try to think about it in low level. You want to think in terms of high level. It's allowed. What that means is this is allowed, so it's right. Continue. Don't stall at all. We're good to go. Otherwise, we'll count our number of thresholds and eventually update our recorder. Yeah, relatively simple.
I do like that if it does get to the threshold, you just allow it anyways.
Which you need to do for safety, right? Otherwise, you don't guarantee progress.
Yeah.
So, I mean, you have this, you may not guarantee correctness, but progress is something, because you don't guarantee correctness anyway. You don't know if you've caught everything, so you might incorrectly stall. Okay, this is really, really simple. This is the kind of thing any one of you could have implemented. So what's the contribution?
It's a future project number 4 for the next cohort.
It's open source. You can go and get the code, so I can't do that.
Yeah.
So what's the contribution? I mean, this is clearly a simple system. It's easier to implement probably than your project 3, which of course all of you are close to finishing
Anytime soon.
Right, this is
It's work in progress.
And your project 3 is simple, but this is simpler. So what's the contribution?
The turning point, they stall it at the exact moment.
Yeah, it's not the underlying system. In fact, even the notion of training based on memory accesses is just what the other techniques that they compare against do. They train against, these accesses that are observed in correct executions and incorrect executions to recognize atomicity violations. So it's a small baby step forward, but it's a big conceptual jump with this idea that there is a turning point. The notion of turning point is huge.
What's that this is new to this big, to the field, the turning point idea, concept?
There were like 6 or 7 tools they were compared against, and none
Most of them were their own work.
They were close to,
Most of them were their own work, to be fair.
Okay.
So
they were their own baby steps. So
yeah, I mean, you can observe this chain of growth where they develop the idea. I mean, that's how science works,
Maybe
right?
they had it planned all along.
No, I mean,
it's
this happens in general with good science, is that you have these baby steps that lead to a better understanding of the problem. And so one of the authors, Shen Liu, has had just a really nice series of works that build on each other and lead to a better understanding of the problem and end up leading to this intuition about how things can work and whatnot. That's just really powerful, I think. And so it's not that any one of these intermediate things was the right solution from the beginning necessarily or something like that, because that's just not how science works. It's this notion of we've made progress, we've done something useful, and eventually you get stuff like this.
It's impressive that you can make small steps towards intuition.
That's how you look?
I don't know, yeah. Like publishing that though.
Well, I mean, it's
publishing small steps towards a intuition concept of like this.
Sure. Yeah. I mean, that comes with just working in the area for long enough. That's the experience, that's right.
Sure.
But if we also look, I mean, we can look at these other techniques, is this the table? Yeah, so this is the breakdown of the bugs and the different patterns. The idea that you can break down these bugs into concrete patterns was one of the other things in one of Shen's earlier papers, ABIO, which is, again, just an invariant detection technique, but instead of to look for the turning point, they looked for detection of the violation. And so
they
there
were
was,
looking at serializability, but
yeah,
they missed one subtle bug which they can catch through the starting point.
yeah, yeah. Well, and they couldn't handle order violation stuff in general.
I'm assuming R-R doesn't mean what is
This means you have
to read them, right?
Okay, so RR pipe the glue, right? So it means that that's
Yeah.
or something. So basically, if a write occurs between two reads, then that's a violation of atomicity.
Yeah.
So the separation is basically the ordering of those.
Separation means that the right thing, yeah, the ordering.
So
You can look at it as a separation of two threads.
RWRD means that there's a read write between a read write?
So the left one is the left thread, which is executing read and then write.
Okay.
The right one is read and then write. They're supposed to be atomic,
Okay.
but if the order varies,
Mhm.
then there can be a potential atomicity problem.
Yeah. So let's throw something into the mix here, just because we got extra time. If you have to leave, I mean, you've got your coat on.
Yeah,
Okay. Yeah, I mean, we don't want a peer pressure effect, but.
It's not really in here present.
Hmm?
Not in present. With pressure.
Okay. Okay. No, I don't want to pressure everybody. Let's think about other types of bugs they don't handle.
Yeah, and then that was
Okay, deadlock. That's one. How locking?
They do one.
Yeah, yeah. I mean, so if you have incorrect mutexes on a single variable int, then they can handle it. What don't they handle? Multiple variables.
Yeah. So there is this paper called C trigger or something, color make, which works on multiple variables, and they claim that you can use that technique and apply it to like integrated with this one, and it should work.
Yeah. Well, it isn't tied to the custom instrumentation stuff, but if you have multiple variables, you can. We looked at atomicity violations on single variables, and we looked at things like race conditions, which are on single variables. But you can also have semantic connections between multiple variables. So you should update, for instance, multiple sets of variables that are different memory locations atomically. This can happen too. If there's some semantic connection between two different variables, and so you want to maintain that relationship, then an incorrect interleaving might overwrite an update of one and not overwrite the update of another, even though individually the updates are correct of individual memory locations. The connection between them is lost. So in order to handle that, you have to abstract this in a more general fashion, and instead of using memory locations, have these notions of variables that should be updated together. There's a
I
question?
feel like that's a very, like, that would have to actually happen quite a bit in anything that's reinitialized.
It's less common than individual variables, I think. I think, but I'm not sure of exhaustive studies on the matter. But yeah, I mean, it is not uncommon to have correlated variables. This much is true.
But I guess this technique can apply to that. Like
You can extend it. Yeah, yeah. So instead of using memory locations, you have update sets, things that should be atomic together.
Yeah.
And if we look at this from the programming languages perspective, there are languages which can enforce that as well by saying these things are an atomic set, things that are related to each other. So let's make sure that the semantic relationships to things are all maintained correctly. There's a lot of work in this area.
If the programmer is amazing and never properly uses their mutexes and make sure that everything is done correctly, there isn't any unavoidable bugs. Like you wouldn't, if you write your program as textbook style, you wouldn't create any bugs, correct?
Are you asking if you wrote your program correctly, would it be correct?
Yeah. Well,
Like
basically, yes. Is there atomic violations even if you do everything properly?
It
Like because of thread scheduling and
Yeah.
stuff like
Yeah,
that.
things that I
Operating
can.
system.
I think I would say by definition, the atomicity, proper atomicity is part of doing things properly. I'm not sure if there's a refinement on this question that can help me.
I'm just wondering if can you always blame the developer?
If there's someone else to blame, maybe the operating system.
Like, if it was a faulty compiler, I could blame the compiler be there. But if it's a developer, like, can every bug be
Blame to the developer.
So you mean, are there compiler bugs that can introduce these sorts of things?
Oh,
Yes.
sure there is, but
Absolutely, and in fact, there's, so the very last paper we're gonna look at, gets at something that isn't compiler bug oriented, but gets at intuitions of how compilers should behave, which is another source of bugs. Which is the idea that if you have a race condition in your code, even if you think it's safe, the compiler is allowed to do things that make it unsafe.
bad compiler.
No, good compiler, bad developer.
Bad developer again.
But the compiler can be buggy in a way that causes those issues. So then the question is, do you have a verified compiler, or do you have a compiler that is known to be correct? There are verified compilers that have been proven to be correct, or for which limited subsets of the behavior have been proven correct.
Yes.
But no one uses them.
This is true. So CompCert is an initiative by France, or by one particular school in France that produces a compiler for which a large portion of the compiler is verified to be correct.
So there's this line in the paper which says, it should be noted that since we implement AI with per variable synchronization, horizontal scalability of the original program will likely not to be constrained by AI. What does that mean?
Could you point me back to that again so I can actually read it?
It's above 3.3, just below the algorithm.
Okay.
This horizontal scalability.
Yeah.
What is vertical scalability?
It's where you put servers on top of each other or beside each other.
That is actually the first thing I thought. Which, I'm curious what the real definition is and see if we can make that work.
You said it wasn't 3.3?
No,
Just above
It's
3.3.
just above 3.
Oh,
Okay, that explains why it's harder to find.
Control F for alpha.
Okay, yeah, gotcha. Fine print. Well, it's all fine print, it's fine. I mean, they don't have to worry about the number of threads. It's all local reasoning, right? So it doesn't really matter how many threads you have.
Yeah. What do they mean by per variable synchronization? Like,
Because they're not looking at the entire application to synchronize. Like if you have a shared variable, you're not looking at everything in the entire application. You're only looking at that specific shared variable and the two threads that are related to it.
That's my interpretation.
Because I think in that regard, horizontal would mean that you could scale that out to many parallel computers, like many threads.
That's my interpretation.
So clusters put servers beside each other.
Or on top of each other.
Okay.
Yeah. Anyway, anything else?
There is a C thread, C trigger.
Yeah. So they do talk about generating tests using these other tools. This might be an interesting thing to know about, but feel free to leave as well. I mean, no peer pressure. There are tools that can explore all the schedulings of a test, or maybe not all schedulings, but relevant schedulings in a structured way. And so that's where you see things like C trigger, and you see things like chess.
That's where they figure out whether something is a false positive or not.
Ideally, I mean, they try to explore all schedulings, but that's for a single input. So it's still constrained. All schedulings for a single input. Or maybe not all schedulings, but again, a wide variety of schedulings for a single input.
That's a fairly methodological way of building your test.
It is. Yeah, so that's how you get a broader sample. Okay. Are we okay? Okay, okay, yeah, we're tapped out, everybody is tired at this point, that's okay.
Yeah, now I have a question. I see with my one in the three.
Where?
Like critique number 6.
Critique is submission enabled for critique number 6?
Today was supposed to be critique number 6.
So it's the number of weeks, not the week. So you submitted, 5 last time.